Hello, everyone. My name is Harman Singh, and today I'd like to share the research I did this past summer on the separation of dijets from W and Z boson decays at linear colliders. This research was funded by the University of Oregon's Summer Undergraduate Research Fellowship and was done under the guidance of Professor James Brau from the Physics Department. So before I hop in and describe my research in particle physics, I think it will be very crucial to give a quick introduction to the Standard Model because it will help situate my research a bit. So what is the Standard Model and why is it important? The Standard Model is at the heart of modern-day particle physics because it describes 3 out of the 4 fundamental forces that govern our universe. Moreover, it describes, classifies, and organizes all the known particles of our universe that make up the matter around us. We can see here on the right-hand side, I have a depiction of the Standard Model. Within it, you can see all the particles and which particles they interact with, which is shown with the blue lines here. As you can see, the Higgs boson seems to be at the center of this model because it has lines that connect it with almost nearly every particle. The reasoning here is that fundamental particles' interaction with the Higgs field or the Higgs boson is what gives it mass. We can see this is why the photon and the gluon don't have lines connecting with the Higgs boson because they are massless particles. The significance of the Higgs boson within the Standard Model makes the detection of the particle in 2012 by the Large Hadron Collider in Europe a crucial and important moment in particle physics because it gave key experimental verification of the Standard Model. However, we gained more questions than we did answers from this detection. Moreover, we know the Standard Model is an incomplete theory of the universe because of the fact it doesn't describe our reality fully. A great example of this is that the Standard Model doesn't contain within it a particle which would be able to describe dark matter. Dark matter is an issue at the forefront of particle physics today, which is the issue that around 85% of the matter in the universe that we can see is dark matter, and we don't exactly know what type of particle or matter this is. So some more background that's particularly focused in my research. So first thing I'd like to talk about is the International Linear Collider. My title page talked about linear colliders, but my research particularly focused on the ILC. So this collider is proposed with detailed designs, but needs funding to be built. So it is hoped that sometime in the near future, people can start building the collider and the physics and analysis can happen afterwards. The ILC hopes to probe dark matter and new physics that lies beyond our Standard Model. However, we know for a fact that the ILC will be able to produce tons of Higgs bosons, which will be a key next step in particle physics to probe whether the Higgs boson's theoretical properties are true. Additionally, the collider is an electron-positron collider, which means it collides fundamental particles with one another, which means that the output and the end product of the collisions will be somewhat clean. It's not going to be incredibly messy and make the analysis job of experimentalists incredibly hard. Additionally, the linear geometry means that we can put in less energy to collide the electron-positron and get more energy out of them. We can see here this depiction of the collider and this scale here to give some sense of how big it is. Every single one of the dots in this line here represent one soccer field, so it's an extremely big machine. I focus on the silicon detector and a component of the silicon detector known as the electromagnetic calorimeter. You can see the silicon detector here, called SID. There's a person here for scale, and the ecal, or electromagnetic calorimeter, is this green portion right here. The other two key components of the detector include the tracker here in red and the purple hadronic calorimeter. So the electromagnetic calorimeter measures electromagnetic energy, the hadronic calorimeter measures hadronic energy, and the tracker measures trajectories. So all three of these components work together to provide physicists with precise measurements. So particularly, they can work together to tell an experimentalist what type of particle has been detected, and the properties of the calorimeters and the tracker are going to be key to be able to measure the energy and momentum of these particles. So particularly, the tracker is significant because charged particles will make a curved trajectory in there. So physicists can immediately tell if they are dealing with a charged particle, and depending on whether the particle deposits most, if not all of its energy in the electromagnetic calorimeter or the hadronic calorimeter, they can also tell what type of particle it is. So I focus on the eCal. The current model of the eCal for the ILC is based off these 13 square millimeter hexagonal pixels. They're analog, so they're able to measure the amount of energy that's been deposited in the pixel. And we can see a picture right here. However, many people have proposed upgrading this model to using monolithic active pixel sensors, or called MAPs, which are 25 by 100 micrometers. However, these pixels are digital, which means that they can't tell you how much energy has been deposited. They can only just tell you if the pixel's been triggered or not. And we can see here that two showers or two particles hitting the detector are much more noticeable and separable here than up above. Because if this red here and this orange yellow are two different particles, they can get confused, and that can impact measurements. People were able to deal with the fact that we can't tell how much energy is measured, just triggered on and off, by using clustering and properties of these clusters, and we're able to regain energy precision in these measurements. I particularly focus on where the current model of these hexagonal pixels can improve, and if this higher granularity of the maps can help. Particularly, I focus on if this can help with jets. So what are jets? So for my conversation about the standard model, you maybe saw some of the particles in there which were quarks. So these are fundamental particles, and we typically find them since they form hadrons like protons and neutrons at the heart of atoms. However, on their own, they're very unstable, and they can quickly lead to clustered showers of particles in a process known as hadronization. So we can see here our electron and positron collide, and from that collision, we might be able to get quarks and maybe gluons and other stuff. Since the quarks here are unstable, they can immediately lead to showers of these particles, which the detector measures that can be somewhat clustered together. However, clustering these particles together makes for much easier analysis rather than dealing with individual particles. Moreover, if all of these particles came from the quark, we know from the conservation of energy and momentum, if we add up all the energy and momentum of these particles, we could get a description of the quark, which is extremely important if you're considering the physics that's going on after this collision. So some of the methods of my research and analysis, a big part of it was simulations. Since the ILC isn't actually built yet, I have to rely on simulations of Monte Carlo simulations of E plus, E minus collisions. These simulations are designed to be extremely realistic and depict particle physics within the environment of the detector. Additionally, I also use particle flow algorithms in addition to the Monte Carlo simulations, which provide me with detector-like measurements to show me what the detector would have likely measured given that event. A comparative analysis between these two can tell me how accurate the detector is. But what I do with these events is I cluster these particles into jets. As we can see here, I have a Monte Carlo and the PFO event, which is the particle flow algorithm. Now this is the truth. We see every single one of these dots here is a particle. Bigger the dot, more energy in the particle, and the color corresponds to which jet it's been clustered into. I particularly focus on two types of events. I focus on events where the electron-positron collide and produce a Z boson and a Higgs boson. For ease of my analysis, I have the Higgs boson decay invisibly, and the Z boson produces a quark and anti-quark pair, which lead to two jets, or known as dijets. I also look at W plus events, where the electron-positron lead to a W plus boson and W minus boson. The W plus boson goes to the two quarks, so I can produce jets and analyze them, while the W minus leads to a muon and an anti-muon neutrino. The reason here is that they're easily removable, so I can focus mostly on this. So the big issue I deal with is how to separate these W and Z events. So of course, when you have these particle showers, you can introduce more error in the measurement of the mass and energy. However, additional confusion gets made since the W boson and the Z boson have very similar masses, which we can see right here. That W has a mass around 80 GeV over C squared, while the Z has a 91 GeV over C squared mass. So the way I'm able to reconstruct these particles, or the information about these particles, is I take my jets that I construct from clustering the particle showers. I use that to reconstruct the original quarks, and then I use that to reconstruct the original W's and Z's. However, as I noted, the close mass leads to confusion. Here is one of the plots I deal with, where I plot out the mass of the W here in red and the mass of the Z. And these masses, again, I get from the jet measurements. And we can see here this region in between is extremely confusing to differentiate between if it's a Z or a W boson. And moreover, for an experimentalist, these plots wouldn't be separated. They'd be together as just one massive plot, and you might not even have two peaks to be able to separate it. So the separation is extremely important for new physics because of the fact one of the events I highlighted was an event where the electron-positron produces a Higgs boson and a Z boson. One of the main goals of the ILC is to measure the Higgs boson and its properties. And if I can identify through my algorithm an event where a Higgs boson is produced, it will be crucial for when the ILC is implemented. Because you might have cases where the Higgs boson decays invisibly, so you have the other particle to rely on. So for example, if I can tell it's a W event, not a Higgs event, people could ignore it for the case of Higgs physics. However, if it is a Higgs event and you can't find particles that relate to the Higgs, we know that it decayed invisibly. However, you can use information from the Z boson to reconstruct some information about the Higgs boson. And more importantly, if we know the Higgs boson decayed invisibly, and if that number doesn't match the numbers predicted by the standard model, that could tell us that we might have something like the Higgs bosons decay into new particles like dark matter, for example. So what is to be done about the separation? Because obviously, from this plot, it looks like it'd be very difficult. However, we can use machine learning to help us separate. So some of the results I have from summer. So for this summer, I have mostly focused on parameters to use for machine learning. So some of the parameters I have here include the combined mass and energy of the jets. However, we saw earlier that was too close. One of the reasons they were too close, I found out later in summer, is because I found a bug in our simulation. Within our simulation, the W boson kept on becoming simulated with a little bit extra mass. And we're currently working on resolving the bug within the simulation to be able to use it in my analysis. Additionally, as if you saw from before, the Z boson is a neutral particle, while the W has charge, either +1 or -1. So that should be something very easy to help us differentiate. However, if you see this plot right here, it shows the truth particles here in blue and the momentum of specifically charged particles measured by the detector, and the red shows here what the detector would have actually measured. And you can see the gap between the blue and the red indicates that the detector is actually measuring less charged particles, and this becomes a more extreme effect as you go to smaller momentum. Particularly, we can see here the fact that if you miss out on some low energy, low momentum particles that have charge, it can toss off your charge measurement. Because if one of these is a +1, -1, it might change your Z boson measurement to being +1, -1. So it can't be used exclusively, but has to be used in conjunction with other measurements. Finally, one of the things we came up with this summer is using jet flavor.
So jet flavor essentially refers to the type of quark that originally decayed into the jet. Depending on the type of quark, the jet might have different properties and physics. Exploiting these unique properties of different quarks and physics can provide us a hint into what type of original particle led to that quark. Here are my citations, and thank you so much to listening to me talk about my research.